This is the last video in the colligative properties section of the solutions chapter. This one is about colligative properties, boiling point elevation, and freezing point depression. So we learned about boiling point in the last chapter, and we learned that boiling point is the temperature when a particular pressure condition is met, when the vapor pressure above the liquid is equal to the ambient pressure, or the pressure of the surroundings. And what we have just learned in the last few videos is that in a solution, the vapor pressure is lowered. That's one of the colligative properties. When you mix a solute in, the vapor pressure goes down. So let's think about how lowering vapor pressure could cause boiling point elevation. So when we lower the vapor pressure, we don't have as much vapor above the solution. We're a lot farther away from our goal of pressure surroundings than we would have been with just a liquid by itself. So that means we need a higher temperature. Higher temperature is required in order to reach our goal of the vapor pressure equaling the pressure of the surroundings. Here's my spelling is proportional to how many people I'm talking to, as well as my algebra. Okay, so we need a higher temperature to apply more heat to the system to get more vapor to finally reach our vapor pressure of the surroundings. And that means our boiling point temperature is increased. So we can describe the relationship like so. So we're going to say delta TB, that's going to be the change in boiling point, equals I, remember that from a few videos ago, the Van 't Hoff factor times a new constant, K sub B, times molality, which is sometimes represented as italic lowercase m. But I can't do italics in pen, so we're just going to write the word. Okay, so remember this is the change in boiling point. So if you want to find the new boiling point, you need to take old boiling point and add the change in boiling point so that the number gets bigger, and that will give you the new boiling point. Okay, this I, that's our Van 't Hoff factor. Remember, that's a count of the number of ionic pieces that our compound is going to break into in solution. This guy, this is called the boiling point elevation constant. Very helpful. This is a constant, and it depends on the solvent. You can look it up in a table, or you can solve for it. And over here we have our good old friend, molality, which we learned about at the beginning of this section, moles of solute over kilograms of solvent. Everything based on more accurate units. And remember, we said that in colligative properties, there's always going to be one term, at least in each formula, that's a how much term, because colligative properties only depend on how much there is. So this formula actually has two. So molality depends on how much, and our Van 't Hoff factor also indicates how much, because it indicates how many ions there are in solution. So this one is pretty straightforward. So let's go ahead and move on to freezing point. So we didn't talk a lot about solids, even though I would have liked to, but you can just believe, take my word for it when I say that the freezing point is the temperature where molecules begin to cool into a lattice structure. Solids are very organized. They are set up and bonded just so in the optimal lowest energy configuration. So that we call this a lattice structure or a network structure. And we know that's true for a liquid. But now we're talking about solutions. And in a solution, we have these solute molecules mixed in. We have these sodium chloride pieces that are in between some of these water molecules. And what we say here is that the solute molecules interrupt the lattice. They get in the way of that nice, perfect, orderly structure with perfect angles and lowest possible energy. And that's really annoying. And that means that more energy is going to be required to move around those solute molecules out of the way to make our super nice lattice of solvent. So there's going to be a lower temperature required. We have to cool it even more than we would normally have to cool it for that lattice formation. Our low energy structure has to be even lower energy with the presence of those solutes. So we need a lower temp. So the freezing point temperature is decreased. This explanation will make a little bit more sense in the next chapter when we talk about entropy. So the formula for freezing point depression, which is delta T sub F, looks very similar. So it's going to be the Van 't Hoff factor, a new constant, K sub F, and the molality. And again, these are our how much factors, the Van 't Hoff factor, and the molality. So delta TF, if we want to find the new freezing point, we'll take the old freezing point and we will subtract the change because we want the number to be smaller because it's a depression. And we'll get the new freezing point temperature. This is Van 't Hoff factor, that's the same. This is the freezing point depression constant, helpfully named. So this is just a different constant that you'll have to look up. Depends on solvent. And this is the molality, just the same as in the previous formula. So this seems a little bit more straightforward than vapor pressure. I wish we could have talked about it first, but you need to understand vapor pressure lowering to understand the shift of boiling point and freezing point. So let's do an example of using that formula. All right, so here's our example. Find the boiling point of a solution of 1 gram of glycerin and 47.8 grams of water. Oh, you can't see that. There we are. 1 gram of glycerin, 47.8 grams of water. Here is the boiling point elevation constant for water. Excuse me, and we need to find the boiling point. So if you don't know what to do, you always start by finding the relevant formula and then trying to figure out if you know any of this information. So we are trying to find the new boiling point, which means we need to know the boiling point shift. We can easily figure out the Van 't Hoff factor. We have this constant. So now we have to get molality, our new favorite, super accurate concentration measurement. Okay, refresher, molality, moles of solute over kilograms of solvent. And our solute is going to be the smaller piece, the glycerin, and our solvent is going to be the bigger piece, the water. So what we need to do is convert the solute into moles and the solvent into kilograms. No sweat. So we'll take our 1 gram of glycerin. We've been doing a lot of glycerin in this chapter. It's a very popular example because it's non-volatile. And non-volatile solutes are simpler. So we use the molar mass of this already, 92 grams per mole. And multiplying through should give 0.0109 moles of glycerin, which is the solute. And then all we have to do for this guy grams of water is to convert that into kilograms. Grams in 1 kilogram. 0.0478 kilograms of solvent. Okay, we are ready to go. So we can plug it back in into the original formula for boiling point elevation. All right, Van 't Hoff factor. This is glycerin. Glycerin is not an ionic compound. It is a non-electrolyte. So I is going to equal 1. We'll plug in our boiling point elevation constant, 0.512. And you'll see that the unit is kind of wonky here. It's basically just whatever unit is needed to cancel out the other units so that we can get degrees Celsius. And then for our molality, 0.0109 moles over 0.0478 kilograms. All right, math happens here. And you shouldn't get a very big number because it takes a lot of solute to shift the boiling point by an appreciable amount. So if you end up with a change in temperature that's greater than 10 degrees, think again and check your math. So our boiling point shift is 0.1 degrees Celsius. But make sure to go back and check the question. The question did not say what is the boiling point shift. It said find the new boiling point. So that means that the new boiling point is the old boiling point plus, so that it gets larger, the change in temperature. So it requires that we know the old boiling point of water, which hopefully you know is 100 degrees. We will add in our shift to 0.116. Oops, not delta, just TB. And we will end up with 100.116 degrees Celsius. And our bullshit test is to check and make sure that our new boiling point is elevated, is higher than our original boiling point, which it is. Okay, so that's the formula in practice. The last thing I want to show you is the phase diagram that we looked at the last chapter. We can actually plot the boiling point elevation and the freezing point depression on the phase diagram. This picture should look familiar. This is our phase diagrams for before. We can use the phase diagram for liquid here. So we've got, or for water, excuse me. So we've got pressure on the y-axis and temperature on the x-axis. We know that the gas exists at the low pressure, high temperature quadrant, that the solid exists at the high temperature, low pressure quadrant, and liquid and the high pressure, high temperature. So if we want to look at the elevation, what we're going to do is we are going to shift this line, right? This is the boiling line. We're going to shift the boiling line down ever so slightly. So we'll put the new point where it hits here, and we'll draw it a little bit lower. And then we're going to shift the freezing line, which is this one. We're going to shift the freezing line towards the left as well. Okay, so this is our new line for a solution. This is a new line for a solution. And then this one is our old line for the single component. All right, so if you don't believe me, let's check. So let's pick a particular pressure and look at how the temperature has changed. So we're going to draw a constant pressure line, which is called an isobar. This is going to be a relatively straight line. I apologize in advance. That is sort of straight. Okay, so let's compare the boiling point at this pressure of the liquid versus the solution. So this one is the liquid up here. Okay, so the place where we hit The boiling line for the liquid is going to be here. So this is the boiling point of the liquid. And the place where we hit the boiling line for the solution is here, boiling point solution. And we can see that from the individual liquid to the solution, that value is increased. It is elevated. So that is true. That's what we expected to see. Now let's look at our freezing point. So this isobar intersects with the pure liquid line right here. So there's our freezing point for the liquid, and it intersects with the freezing line for the solution right there. Freezing point, solution. And we can see that, yes, in fact, from the liquid to the solution, the freezing point goes down. There's a freezing point depression. So this is something you should be able to draw given a phase diagram. So that is the end of our discussion of vapor pressure, freezing point depression, and boiling point elevation, which are all colligative properties that only depend on how much of a substance there is and not on what kind of a substance it is.